Okay. Hi, everyone. My name is Mike Lorbello. I am an iOS engineer here at Lyft on our mobile infrastructure team. I was kind of laughing about this earlier. Actually, a lot of this talk is about how to not use JSON anymore. So make up your own minds, I guess. I'm going to be talking a little bit about Lyft's networking stack on mobile as it is today, as well as kind of how we've started rethinking where we can make improvements and then where we're taking it in the future. So to give you a high-level overview of where we are today, I'll give you a side-by-side with iOS and Android. So to start off, we currently define our endpoints in YAML and Swagger, and this lives inside of one GitHub repository today, which is basically a container for information on all of our client-facing endpoints. So this would include metadata you can send in a request, what types of responses we can send back, any errors that might be expected to be returned from certain endpoints. And I'll come back to that a little bit later. As you might expect, we currently use HTTP as our transport layer, and we send JSON today for the most part over that. In most cases, we do gzip it, so we get some sort of benefit from that level of encoding. Now, where iOS and Android really differ today is on the mapping layer, where we actually take the data we get from the server and convert it into a model on the client. So on iOS, we currently use a framework that we have actually open sourced. It's called Mapper. And this mapper is used to basically take dictionaries of JSON data and map that into strongly typed Swift structs that you then pass around basically throughout your day-to-day in the code base. Android took a slightly different approach, and they actually depend on that YAML and Swagger and generate data transfer objects, which are basically strongly typed models that are closely tied to this YAML and are basically only used for mapping from the network layer into something that's strongly typed on the client. So it's very strongly tied to that YAML and Swagger, and then they then take that and handwrite their own models on top of it. So they transform it however they need to, and then use that elsewhere in the code base on the day-to-day. And that kind of abstracts out the separation of concerns between the data representation on the server and then how we represent it on the client. Now, some of the trade-offs I'd like to point off here are HTTP1 is really well supported. Pretty much anything you come to will support it, but it does have some limitations, which I'll get into a bit later. Secondly, YAML and Swagger is pretty simple to write, but it doesn't act as a single source of truth. Now, what I mean by that in this case is iOS, as given in my previous explanation, does not actually respect the YAML and Swagger definitions that we have. And basically, that's a problem because iOS and Android are kind of out of sync, or they can be out of sync because iOS engineers use this as more of a point of reference, whereas Android is strongly typed to it. And the other downside here is that our servers actually also don't really respect the YAML. They also use it as a point of reference. So there's only one of these three places that use this data that are actually depending on it to be correct. And the third point I want to make is that JSON mapping is really easy to iterate on. It's basically adding one line of code if you want to add a new field to your model or add some new data, but it's also pretty fragile. And that's the one I want to focus on for the time being. So we've actually had incidents in the past where either the server will send unexpected data, and then we won't find out until runtime because there's no really way to find that out at compile time. And so we won't be able to decode these models, and we'll just get nothing back. We've also had the reverse, where the server will send data that we're not expecting on iOS. Maybe some server engineer made a typo, and we get the same result. So these things can happen on both the client and the server, but either way, we end up with the same result that breaks the mobile clients. So this kind of got us thinking about where can we improve this structure today? What can we do with our current networking stack on iOS and Android in order to make this more reliable and get us to a state that's less error-prone? So the first thing that comes to mind is we could switch to strong types that are consistent across both mobile platforms as well as the server. So as we tried to approach this, we came across something called protocol buffers, which are commonly referred to as protobufs. And if many of you are not familiar with this, I wasn't very familiar with it until recently, but Google's very wordy explanation is a language-neutral, platform-neutral, extensible mechanism for serializing structured data. That is a huge mouthful that probably you had to reread to understand any of it. But essentially, it means that protobuf allows you to define a model. So you can think of it as a struct. You define that in one place, and then you can easily translate it into multiple languages. And it gives you that functionality under the hood where you basically define something in one place, and you can generate Swift files or Java files or Python or Go or whatever the languages that you happen to be using in your project are. And the way that works is you define something similar to this. So you would define a message, for example. As you can see, this whole file looks very similar to a Swift struct, and that'll play in a little bit later. But you would define something like a message, and within that, maybe we have our own custom type called a ride type, and then a couple system types that are just doubles here, which are latitude and longitude. And you can ignore the number representations. Those are more of just implementation details of how protobuf stores unique keys. So if you were to take that protobuf structure and generate Swift from it, you end up with actually a struct. So you end up with something very, very similar to what you initially typed. But you can get this same representation in Java. You can get the same thing in Python. And again, it's all provided for you through their tooling. So we can actually take that a step further and prefix these with something like DTO or data transfer object to give us a little bit more parity with Android. Just a quick FYI on how we get from a protobuf file to Swift or to Java. Basically, there's a command line tool called protoc that you're able to run a command on it. You run protoc, and then you tell it the language that you want it to output, which is basically the name of the plugin, and then you hand it the path to your protobuf file. And then you end up with something like this. So for example, protoc, Swift out, name of the file, gives you this thing, .swift. So some of the key wins you get from protobufs right off the bat are, one, it's strongly typed, right? You have this structure. You're not passing around JSON anywhere. The second part is that this actually provides a great amount of compression if you were to send a protobuf representation over the wire. And thirdly, it provides code generation for numerous languages. So as I said, you have one representation, and you can kind of generate different language representations based off of that definition. So great, we have strong types, but these types still only live on the clients, right? This doesn't actually explain, this doesn't solve the problem that I mentioned earlier where these clients and the servers are not speaking the same language. So how do we actually use them? Well, protobuf is more of a wire format, right? But we still need some sort of transport layer to send these things between services. So we could actually use HTTP and JSON. And that would work fine, and that is a perfectly acceptable approach. Protobuf is pretty extensible, so you could totally do that. However, we're looking for something a little bit more extensible. So in our case, we're actually looking for something that might support streaming. So if we're going to be redoing our networking layer and building something to set us up for the future, we want to get us to the best state we can be at. So an example of where Lyft might use streaming might be getting the driver's most recent location, right? So let's say you request a ride, and you're sitting there waiting for your driver. You're looking at your phone, and you can see the driver's car moving along the map. Basically what's happening there is we're asking the server every few seconds, where's the driver's car? Has it moved? And then we draw that on the map when we get the response back. As you can imagine, if we're waiting a few seconds in between each network call, we're adding some latency, and the driver might already be there, and you won't find out till maybe 5 seconds later, or if you're in a really low connectivity zone, it might take even longer. If we're able to actually support streaming, basically that paradigm shifts, and we end up with the server telling the client when the driver moved as opposed to us asking for it. So we get the information much, much quicker, and it also avoids extra latency of us making requests and asking for things that may not have changed. So some of the things that we investigated, the first off is RPC, which stands for a remote procedure call. So ignoring the name, the easier way to think about this is basically you're calling a function on a remote service. So it's kind of shifting away from the idea of I'm making an API call on something else and I'm waiting for that thing to happen, and then I do something with the response when it comes back. Instead, you should think about this as more of calling another function somewhere else in your code base. And in this case, you're actually calling it using protobuf messages. So you're calling it using those strong types that we generated earlier. So to illustrate this a little bit, let's say that we wanted to make that request from the client, right? So we wanted to actually get new information on the driver's location. The client would initiate a request and basically call a function or an RPC stub with that information. So you call a function somewhere else in your code base, and under the hood, RPC actually packs that struct into a protobuf and then passes that on to our servers. The server then unpacks that same protobuf data, but this time it encodes it into a Go class or a Python class or whatever language our service happens to be written in. And from this point, it has the exact same representation that the client knows about. So they're able to actually speak the same language, and the server can go do what it needs to do, and then return that new representation as it knows about it back to RPC. And then RPC does that same encoding, but in reverse, back to the client, and the client gets back a Swift struct. So throughout all of this, there's actually no JSON encoding, there's no manual mapping for things, all of it happens under the hood. And the really powerful thing here is that each system is able to speak the same language. So you have one file that defines both the function names as well as the models. And you can look at that file, or you can look at one of the implementations on any of those platforms of the file and have a pretty good understanding of how the whole thing works together. So here's an example of what an RPC quote-unquote stub might look like. It looks very similar to a Swift class. Basically, you define a service, which, like I said, is very similar to a class. And then inside of that, you define an RPC. So this will actually turn into a function when you generate Swift or Python or something else. So in this case, it's a function called getLocation, and it takes a driver location request message, or in this case, a Swift struct, and then it returns a response. So I'll get into how that translates to Swift in a minute, but first we needed to figure out what options do we actually have. So RPC is a protocol, but we need something to actually implement that functionality for us. So two of the big contenders are gRPC and Thrift. We opted to go for gRPC, which is basically Google's version of an RPC implementation. So the way Google implemented this is they basically built most of this functionality they wrote it all in C, and then they built this into a library that they called their gRPC C core, which is the core functionality for gRPC written in C. Once they had that, they built out many other language representations of this that basically wrap this C core, but expose public interfaces in their native tongue. So for example, you could have Objective-C that exposes Objective-C APIs, but under the hood, it's still talking to the C core, and depending on that. So they're actually able to make changes in one place, and most of these languages can get the benefits from that with little to no changes. And this is one of the reasons that we went with gRPC. So one, right out of the box, they support a ton of languages. Two, Google is heavily backing this. And three, they actually have great support system and are regularly updating this. If you look at their repositories, there's a ton of commits on them. They have very strict release cycles. They have betas every few weeks. They have production releases every 6 weeks. I think they also have phone calls you can join every 2 weeks that are just like, here's the state of gRPC, here's where we're going. So it's actually really nice. One thing you might notice on this slide is there's no mention of Swift, though. So this became a little bit problematic as we were thinking about integrating this. So as we did a little bit more investigation, we found that there actually is a Swift gRPC repo, but Google has explicitly marked it as experimental. So that's kind of a little concerning when we are thinking about shipping something to production. So we had a few options, right? The first option was we could just use the Objective-C version of gRPC, which would work. That's fine. However, our entire code base is in Swift. So if we add a new Objective-C dependency, that's not great from like a tooling perspective, but then also we're forced to generate Objective-C files instead of Swift files from protobufs. So that's introducing more and more Objective-C code as we use more pieces of gRPC and as we migrate our events, our endpoints over. And then the second part of that is when you have more Objective-C code mixed with Swift code, that's moving away from our paradigm of all Swift, but then it's also introducing longer compile times. It's introducing more context switching for engineers. They have to go switch between languages on a daily basis. So this really wasn't a great thing that we wanted to go with. So we were pretty much on the path to just try Swift. So that said, we went and we reached out to Google, and they're actually really excited about having us try it out. Their team is really great. They're super happy to work with us and to work with other people who are working in this community. And so we basically took this and we started implementing it in our app. And we ran into a few things because it is experimental, but we upstreamed fixes for all of these as we built it out. And there's a ton of people actually contributing to this. There's a lot of people working on this. It's a pretty well-supported repository. And there's definitely a path forward to getting this into becoming an officially supported gRPC language. So that's actually pretty exciting. So taking a step back, when we actually use gRPC with the services that we mentioned before, what does that actually look like when it comes to Swift? Well, if we take another look at the previous definition we had in protobuf for this service called getLocation, and we run the command line tool on it, we end up with something like this. So we get a generated Swift class, which is a service client, and it exposes a function called getLocation. And again, it takes that same model representation we saw before. And similarly to how you'd expect with a URL session, natively in Swift, it gives you back a completion closure, but instead of just an sdata or an error, it actually gives you a strongly typed response, and it gives you an error back and a call result. So to recap, a couple of key benefits with gRPC. First, it utilizes protobuf. It's actually designed to work with protobuf, so it works really, really well, and it gives you these strong types on the wire, and it encodes them into really small payload sizes as opposed to JSON. Secondly, under the hood, gRPC uses HTTP2, which maintains one single connection. And you don't really have to reconnect between endpoints, so you end up with it being faster. And HTTP2 also supports streaming, which meets our previous requirement, which is really nice. And furthermore, gRPC actually takes advantage of that and provides first-class support for streaming. So you can define either a unary endpoint, which is more or less what you think of as the classical HTTP request, where you post a request, wait for a response, and then get that response back. Or you can use it to implement streams, where you basically, bidirectional in this case, means you can send data up continually. So you can basically keep sending data over a stream, and then the server can keep sending data back to you. So this is much, much faster, and it allows you to send data back and forth more easily without having to call a new function or start a new request entirely. So when we implemented gRPC, we took a few steps to kind of make our lives a little bit easier. And the first one of those things is we introduced the concept of validation on our end. So when we take a look back at the very first protobuf message I introduced, you'll notice at the bottom we have a double value for pickup latitude. And thinking about latitudes, it's a double value, but there's a very finite number of valid latitudes, right? It has to be between -180 and +180. Anything outside of that is not an actual valid latitude. Natively, protobuf doesn't really provide support for being able to guard against this. It basically just happens whenever you were to check against it. So we added this concept of validation rules. And that's actually open sourced on GitHub by Lyft, which you can check out. The name of the project is at the bottom right. But we can add these validation rules to double. And for example, we can enforce that this is greater than -180 and less than +180. And essentially, when we run those generators on these files, that allows us to generate Swift code or generate Python code that inside of that performs these type of validations in that language that enforce that these types keep these values within those ranges. And there's a ton of different validation rules. This is just an example of one of the more primitive ones. The second piece that we used to build on top of gRPC and protobuf was a little bit of automation. So normally you would take a proto file, and when you run the command line tool on it, you end up with a set of Swift files, and then maybe you end up with some Go files and some Python files, which is perfectly great. Like, that works totally fine. But as we start growing and as we add more endpoints to gRPC, this number of files kind of builds up. And it's more for us to compile every time a developer builds the app. But then also there's a lot of files and it's hard to find them. B, you have to remember not to edit these because they're all generated, and if you modify them, they're just going to get overwritten next time they're generated. So something we decided to do is basically pre-compile sets of these into modules. And then we end up with these modules that we can then import from elsewhere in the code base. And so that leads us to the last change that we built on top of protobuf and gRPC, which is abstraction. So as I've shown before, you could use the generated code that comes right from gRPC and protobuf. But we decided to add some wrappers on top of that to make our lives a little bit easier. So in addition to the .grpc.swift or .pb.swift files, we're also generating these wrapper files. And essentially what these do is we'll import our dependencies, and then we'll kind of wrap all of the call sites with some of our own convenient stuff. So as you can see, this function called getLocation still takes that same request model, but under the hood, it handles trying and catching and some error handling and retrying logic all for you under the hood. And then it exports that function publicly so that on a normal engineer's call site, they can basically import that module and just call the function directly. So this has two big wins from our perspective. The first is you no longer have to directly import Swift gRPC or Swift protobuf from most call sites throughout the app. All of that is contained in these pre-compiled modules that we have. So that kind of hides away the implementation details of what's happening under the hood. So we could actually switch out RPC or something else. As long as we keep the public interfaces the same, none of the call sites will actually have to change. The second piece of this is that it kind of reinforces that concept that RPC pushes of you're calling into another function in your code base and not specifically like making an API request. And as you can see from this, it doesn't really look a ton like you're making an API request aside from the words request and maybe response. But it's basically you're calling into something and just getting a closure called back. So going forward, some of the things that we're planning to do with gRPC and our new networking layer are, first off, we're currently piloting this rollout on our analytics. So the reasons we picked analytics as opposed to some of our other endpoints is our analytics is one of our highest traffic endpoints from the client, so we send a lot of data up. So it's good to kind of load test that. And secondly, it's really easy to shadow analytics data, so we can actually send our analytics over HTTP as well as over gRPC and kind of compare how those work. So we can compare the SLAs of how long these events take to get up to the server. We can compare the payload sizes, and it's not a huge deal if some issues arise because we're just shadowing them. We're not actually using them for production just yet. The next step is we're planning on rolling this out to new endpoints and eventually all of our endpoints. And then the biggest milestone after that will be starting to use the streaming functionality of gRPC. So this will allow what I mentioned before of basically shifting to a world of push instead of pull, where the server is handing the client information as it becomes available, as opposed to the client sending information up and asking if something changed. And this not only makes a better experience for our users because it reduces the latency of the information that they get, it's always more real time, but it also saves a lot of network, it saves battery, all of those types of things. So I would highly recommend checking out grpc.io. It has a lot of great information. Their documentation is really good if you're just curious about what gRPC is or what protobufs are. I would highly recommend checking out protobuf, even if you're going to use it over HTTP. It's still an awesome system to use. And that's about it. Here for questions.
All right, I'm going to run after Alexis here.
Hi, I was wondering what impacts this had on other ways that you interact with that code. So one of the things people like about JSON, I don't know if it's a great thing, but one of the things people do like about it is it's sort of human readable, but all this super compressed binary stuff isn't as much. And one of the things maybe not so great about JSON is it has no support for versioning. I seem to recall gRPC might have something like that. So I don't know if you've just could say a word about how you've found you needed to adopt new tools to work with this, or needed fewer tools to work with this, or something like that?
Yeah, those are actually great questions. The first one we were talking about just before this, actually. So we have an in-house tool that more or less acts as a proxy. So we're able to inspect network traffic coming from our iOS simulators and kind of see what the client is sending to the server. That breaks when it comes to gRPC because of what you said. It's highly encoded, and you basically need the protobuf model to be able to decode that. So we are going to have to build some new tooling for that. That'll basically allow us to decode that traffic. We haven't built that yet because we haven't rolled it out to all of our endpoints, but it's definitely something that we will need to do. The second piece of that I'm sorry, what was the second part of it?
Schema versioning, and if you're changing the way you do that. Sorry, schema versioning, and if you're changing the way you do that, or...
Yeah. So versioning, protobuf supports versioning pretty well in that, so earlier in the slides, you could see there were integer values assigned to each field. Essentially what that acts as is those numbers, once they're shipped to production, are basically reserved. So clients will always have default values. Proto 3, which is the current version of protobuf, all fields are actually optional, so they all provide default values for you. So new clients can ship without having a representation sent to them, and they'll be able to just supply default values. And then they're backwards compatible in the way that you're never allowed to actually delete a field. You can remove the field and not, you can remove the field and then reserve the original key that was assigned to it. But you're basically always guaranteed safety of these models because of how protobuf is structured and how it decodes those messages.
Next question.
Yeah, the code example, sorry, microphone. The code example that you gave about basically doing the API call with protocol buffers doesn't really look that different from like a regular REST, like JSON API call when you actually look at the function that you're going to be calling. And specifically with streaming, I'm wondering like, does that same interface still work? And if so, or if not, how you have to change it and think about calling like the get location in a different way, for example?
Yeah, that's a good question. This does change a little bit with get location. So in this case, the example I gave was basically a unary call, so it's like a one-off, basically, as you mentioned. The way you would handle streaming would be, as you can see, is creating an instance of driver location service, which is that kind of service that handles the communication layer. The way you would handle that is you would likely hang on to an instance of that service, and when you're receiving data, the way gRPC handles it is it basically keeps calling back this closure that you provide it. So the completion closure can basically get called multiple times with each piece of data, and it gives you a different state within that result. So that's kind of how they handle data coming down. And then data going up is somewhat similar. You basically call the service again, but hand it more data. So it is a little bit different. It basically changes how you treat completion handlers from it's not really completion, it's more of like an update.
Cool. Hey, so I had two questions. So with gRPC, there's C core. I'm curious, where is the networking component handled? Is that in C core? Or, you know, because given different platforms, they'll have different network stacks, et cetera.
Yeah, the vast majority of it is handled in the C core. There have been talks, I know, about writing full implementations at like a higher level. I know that something that's been talked about on Swift gRPC's GitHub pages are basically replacing pieces of the networking stack with like Swift NIO or the new networking framework that was announced at WWDC. So they're definitely like on top of that, and I think they're excited to use some of the new iOS-specific frameworks. At the moment, I think most languages try to maintain their connectivity to the C core, but it doesn't seem like they're opposed to deviating, if that makes a much better experience.
Yeah, that makes sense. Cool. And then my other question was around compression. So, you know, before when you're kind of comparing and contrasting, you mentioned gzip. I was curious if there's a specific compression that was being used for gRPC, or if when you say compression here, you more just mean like it's binary, so it's really small and therefore very like compact.
Yeah, proto representations are by nature smaller because they basically use those integer keys as opposed to JSON like string keys. So that makes them smaller. And then there are actually different encoding policies you can give to gRPC. So one of them is actually gzip, so it can gzip the payloads. And then there's a couple other arbitrary ones in there.
Cool, thanks.
Yeah.
Okay, let's go with you first.
Hey, I was wondering if you also considered GraphQL along with Thrift and protobuf, and if so, why you went with protobuf?
I don't think at least I wasn't involved in that particular conversation. I don't know that we really considered it. I think there are teams that use it a little bit, but that's mostly server to server. I think client server, it's not super useful in our case, primarily because there's not a lot of like dynamic querying that we really need to do for the Lyft use case. But I have seen that we do use that server to server for some of these. But I don't think that was really considered a ton for the client perspective.
Thanks.
Sorry, just a quick follow-up on the C-Core question.
Yeah.
I was wondering if that, if you thought about how that impacts your ability to do networking in the background or things that only the system can provide, and if you use it for like large payloads, like images or videos, or I guess you wouldn't for Lyft, or if it's something you imagine confining only for smaller data payloads. Thanks.
So the ability to run requests in the background?
Yeah, like a background task. If you were, say, uploading a very large video file, that's probably something you couldn't do through C-Core. If you need to use system API. I'm just wondering how it affects like more edge cases like large payloads and networking process in the background.
Yeah, I'm not 100% sure on that one. I would assume at the very least, if we knew that requests were still in flight, we could start our own background tasks since we kind of wrap it in Swift, and Swift does the same thing with Swift gRPC. But with respect to it currently handling that, I'm not 100% sure, to be honest. I would have to check.
All right, thank you very much, Michael.
Thanks, guys.